determine magnetic field due to current. So Biot-savart performed a lots of experiment in order to determine magnetic field due to current carrying conductor. After announcement of Oersted experiments outcome, because Oersted just given the concept that a current carrying conductor exhibits magnetic effect around it, but Oersted could not explain about the strength of magnetic effect, that is quantitative measure of magnetic field due to current was not explained by Oersted. Therefore, Biot and Savart and their co-worker, co-associates started performing experiment in order to measure a strength of magnetic field or magnetic impact produced around a current carrying conductor. So Biot-savart divided a current carrying conductor virtually into small pieces, and each pieces is called elementary part of current carrying conductor. And current along with the length of elementary part together is called elementary current or current vector. So first of all, Biot-savart law, Biot and Savart determine the magnetic field due to elementary part of the current at a point P at a distance R, and then they integrated or add up the magnetic field due to each and every part of the conductor. And so we come to know the magnetic field due to whole conductor. So first of all, try to understand. According to Biot-savart, the strength of magnetic field due to elementary current, that is elementary part of the conductor, is dB and is due to a small current element dl carrying a current I at a point P, which is at a distance R from the elementary current, is directly proportional to current passing through the conductor, also directly proportional to elementary length of the conductor, and then directly proportional to sine of angle between current vectors and position vector of the points where magnetic field is to be determined. And inversely proportional to a square of distance between the elementary current and the point where magnetic field strength is to be measured. So mathematically, Biot-savart law is stated as the magnetic field dB due to elementary part of the current carrying conductor is directly proportional to current I. Second one is dB is directly proportional to elementary length of the conductor dl. And third one is dB is directly proportional to sine of angle between current vector and position vector of the point where magnetic field strength is to be measured. Hello? 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 So Okay. Now, and inversely proportional to a square of distance between the point where magnetic field is to be measured. And so combining all these four statements together, we get dB proportional to IDL sine theta upon R square, or dB equal to K IDL sine theta upon R square, where K is proportionality constant and its numerical value has been determined using experimental activities, and K has numerical value mu naught upon 4 pi, where mu naught is the magnetic permeability of the vacuum. So one step more, we can derive Biot-savart law in vector form. Hello, कनेक्ट नहीं हो रहा है, कुछ बच्चे तो कनेक्टेड, देखिए आपका पासवर्ड है 07959। हो सकता है नेटवर्क का प्रॉब्लम हो, लेकिन मैंने तो उसको देखो ये वो लोग भी नहीं ज्वाइन किया है ना। अच्छा अच्छा, देखो मैं अब क्लास से यहाँ कंटिन्यू कर दिए थे, रिकॉर्ड तो हो रहा है ओवरऑल। देखो ठीक है, मैं ऐसा करता हूँ कि आपको फिर से रिपीट करना पड़ेगा। ठीक है, देखते हैं, ट्राई करो। क्लास तो ऑन है, मैं देख लेता हूँ क्या प्रॉब्लम है। So now a vector form of Biot-savart law, as we have derived mu naught upon 4 pi I dl sine theta upon r square. So mu naught upon 4 pi is a constant. Now we take the non-constant part of this expression, say I dl sine theta. So if you take I dl as one vector quantity and sine theta always involved in the cross product of two vectors. So here only one vector is here, ideal, and another vector is not there. So if you insert a unit vector in between ideal and sine theta such that its physical value does not change, because unit vector has magnitude 1. So if you multiply this expression by 1, the numerical value of expression will not change. So in place of 1, we write unit vector r cap here, you see. Now you know that vector A cross vector B equal to vector A mod of vector A into mod of vector B into sine theta. We know well. Mod of vector ideal equal to ideal, and mod of vector r cap equal to 1 into sine theta. So ideal into 1 into sine theta equal to ideal sine theta. So in place of ideal sine theta, we can place ideal vector cross vector r cap upon r square. So this is the vector form of Biot-savart law. Now we place main vector, a position vector r in place of unit vector. You know that unit vector r cap equal to vector r divided by magnitude of vector r. That is vector r cap equal to vector r divided by mod of vector r. So mod of vector r can be written as r simply. So already there is r square, and in place of r cap you write vector r divided by r. So r square into r becomes r cube. and your final expression is this one. So this is the vector form of Biot-savart. Mu naught has numerical value 4 pi into 10 to the power minus 7, and Tm, that is Tesla meter per ampere or Weber per meter per ampere. Now, as we see that Biot-savart law is expressed as a vector product of two vectors, say current element vectors or current vectors and position vectors. Therefore, its direction can be determined by right-hand thumb rule because it is a cross product. So direction of magnetic field at point P can be determined in the same way as the direction of dl cross r, which can be determined by the right hand screw rule or right hand thumb rule. So a magnetic field at point P, if you apply right hand thumb rule, appears to be entering into the plane of the figure. So wherever magnetic field appears to be entering into the plane of figure is denoted by cross at the point of entering. And wherever magnetic field coming out of the plane of the figure is denoted by dot. So here magnetic field line enters into the plane. Here magnetic field line comes out of the plane and forming a closed loop. So here current element is a vector quantity whose magnitude is the vector product of current and the length of a small elements of the conductor having the direction of the flow of current, and current vector is denoted by uh, a product of current and displacement dl. That's why it is called I into dl together is called current vector. But when you separate this I into dl, then I is no more vector. Now come to the point application of Biot-savart law. Application of Biot-savart law. Magnetic field due to a straight wire carrying current. According to Biot-savart law, we take infinitely long current carrying conductor and we have to find out magnetic field at point B due to this is infinitely long current carrying conductor. So first of all, we have to apply Biot-savart law. Before applying Biot-savart law, we have to take a small portion of this infinitely long conductors, say dl, and we have to determine magnetic field at point B, at point P due to this elementary length of the conductor. And then we will integrate the magnetic field obtained due to elementary part of the conductor in order to obtain the magnetic field due to entire length of the conductor. So first of all, using Biot-savart law, magnetic field due to elementary part of the conductor is denoted by mu naught I dl sine theta upon 4 pi r square. It is well known to you. And here, looking at the figure, this is elementary part of the conductors, and even you can say this is a current elements or current vector. Current vector is directed in this direction, and this is the position vector of the points where magnetic field is to be determined. So this position vector is r, and position vector and current vectors make an angle theta. You see here. So here is sine theta. Now A is known, that is distance from the perpendicular distance from the current carrying conductor and the point where magnetic field strength is to be determined. So this is known. This is known. but R is not known. This is arbitrary. So we have to eliminate R in terms of known quantity. We know that here sine theta equal to A upon R, where sine theta is this one. So this is perpendicular. A becomes perpendicular and R becomes hypotenuse to this. So sine theta equal to perpendicular upon hypotenuse. Similarly, if you look at this triangle and taking this angle phi, so position vector makes an angle phi with the A. So in this triangle, this phi is angle, then this will be perpendicular. That is, L will be perpendicular. In this situation, L upon R, L upon R equal to sine phi, but here we have to take cos phi because A and R to be correlated. So cos phi equal to base upon hypotenuse. So base is A and R is hypotenuse. So cos phi equal to A upon R. So these are the equal. So R equal to what? A upon cos phi, because R is a known things that is to be eliminated in terms of known things. So phi can be varied from 0 degree to 90 degree on either sides. So we take the elementary parts. Now we can take the phi. So R has been eliminated, and putting this value of R here, A upon cos phi. Next thing is DL is to be eliminated because DL also arbitrary things. So tan phi equal to L upon A. Okay. So tan phi equal to L upon A. So L equal to A tan phi. Now DL equal to differentiating both sides. So DL equal to A sec square phi into D phi. Now eliminating DL by A sec square phi D phi and R by A upon cos phi, we get mu naught 4 by substituting for R and DL in equation this one dP, we get the expression of dP, we get mu naught upon 4 by I cos phi d phi into d phi upon A. And now magnetic field due to whole conductor. This magnetic field is due to elementary part of the conductor DL. So now in order to obtain magnetic field due to whole conductor, can be obtained by integrating under the limits phi 1, because this side it get extended up to phi 1 and this side get extended up to phi 2. So we integrate this one. So dB becomes B after integrating, and here angle will be negative because clockwise taken to be negative angles and anti-clockwise taken to be positive angles. So phi 2 will be positive and phi 1 will be negative. Okay. So here taking the terms constant outside the integral. So here mu naught I upon 4 pi into A taken outside the integral. Only the quantity to be integrated is cos phi. So cos phi into d phi, integration of cos phi equal to sin phi minus sin phi, and here you get the result is this one. This is a general expression for magnetic field due to a straight current carrying conductor. Here length is not asked to be infinite or finite. So this is general expression. It can be used for both finite and infinite. Now case is to be implemented here that if the conductor is infinitely long, then phi 1 and phi 2 becomes 90 degree. So placing the value of phi 1 and phi 2 90 degree, we get magnetic field mu naught into 2I upon 4 by A. So we get mu naught I upon 2 pi A. This is the final result. So you see here the magnetic field increases if distance of the point from the conductor decreases. That as we move away from the conductor, magnetic field strength go on decreasing and becomes zero at infinite distance on either sides. Direction of magnetic field B is same as that of the direction of vector dl cross r, which can be determined by right hand thumb rule or a screw rule. Now it is perpendicular to the plane of the diagram and entering into the plane at P. That is, magnetic field is perpendicular to the plane of the diagram. That is here, you see here. Here. It is perpendicular to the plane of the diagram. Conductor lying in the plane, but magnetic field will be perpendicular to the plane of the diagram. So here perpendicular. So perpendicular could be two types, either into the plane or out of the plane. So here this side's into the plane. When we come to this side, out of the plane. So into the plane is denoted by cross and out of the plane is denoted by point, dot. So magnetic field lines, pattern of field line is obtained by applying right hand thumb rule. If current is coming out of the plane, then you apply right hand thumb rule. Here thumb is pointed towards the direction of current, then curled finger is give you the direction of magnetic field. Here magnetic field will be anti-clockwise. On the other hand, if current is pointed into the plane downwards, then magnetic field will be clockwise. Just you see in the figure. Next application is magnetic field due to a circular loop carrying current. Before I discussed here that magnetic field due to infinitely long straight current carrying conductors. And this is the general expression. If conductor is finite, then value of phi 1 and phi 2 will be less than 90 degree. And you can place the value of angle and you can calculate magnetic field due to finite straight conductors. Now, instead of taking a straight conductor, here we take curved conductor. So you see here conductor is a straight, then magnetic field is concentric circle around the straight conductor. Now, if we take current carrying conductor itself is a circular loop, then magnetic field at the center of the loop appears to be straight and will behave as a bar magnet. A single current carrying loop will behave as a bar magnet with one face as north pole and other face as south pole. The face where current appears to be moving anti-clockwise will behave as a north pole, and the face phase where it appears to be moving, current appears to be clockwise will appear as a south. So try to understand here. Again, instead of a straight conductor, we have a curved conductor. And now we have to find out magnetic field due to this curved conductor or circular conductor or a current carrying loop. The same mechanism is to be applied. Here magnetic field due to circular loop carrying current. So at a point on the axial line, say at point P, we have to find out magnetic field due to this current carrying loop. So apply the Biot-savart law, applying same formula. First of all, we divide the loop into a small elementary parts of length dl, and then we find out magnetic field due to this length, and then we integrate the magnetic field obtained due to the small length of the loop, and we will get the entire magnetic field due to entire loop of the conductors. So here, by looking the figure, you see this is the position vector of the elementary. This is the position vector of the points where magnetic field strength is to be determined, and dl is the length, elementary length of the conductor. So this distance r is the distance between the current carrying conductor and the point where magnetic field is to be determined. And this A is the radius of the circular conductors. And from the center of circular conductor, the point P where magnetic field is to be determined is situated at a distance x. So here x could be variable, so are also variables, but age constant. Now try to understand, if we find out magnetic field at point P due to this elementary current IDL, you see that magnetic field at point P will be perpendicular to the plane of the figure. As we have already shown you that in this figure, current carrying loop is line. So magnetic field must be perpendicular to the plane of the figure. So here, this is the magnetic field. Now we resolve this magnetic field into two components. Say this position vector makes an angle phi uh, with the x-axis. So, and this is the perpendicular to the x-axis. So you can resolve this dV into two components, dV cos phi and dV sin phi. You see that half portion of the circle will have component in this direction and half portion of the circle will have component in this direction. As figure is symmetrical, therefore, these two components will cancel out each other. So only components in the horizontal direction or along x-axis will add up together to contribute to magnetic field at point P. The plane of the coil is considered perpendicular to the plane of the diagram. Okay, this is the diagram. Say, plane of the coil is perpendicular to the x-axis such that the direction of magnetic field can be visualized on the plane of the diagram. Therefore, magnetic field will be visualized in the plane of the diagram. So at point C and D, current element X, Y and X prime and Y prime are considered such that the current at C emerges out and at D enters into the plane of the diagram. So remember here, direction of current at this point and at this point is reverse here and here. So magnetic field due to this two elementary part of the current at point P will be equal in magnitude but opposite in direction. Therefore, they will cancel out each other. The vertical components, only components horizontal to the x-axis or parallel to the x-axis will contribute to the magnetic field. So look at dB equal to mu naught upon 4 pi ideal sine theta upon r square. This is well-known expression for Biot-savart law due to elementary current ideal. And now here we have to find out theta. What is theta here? You know that theta is the angle between the current vector and position vector. So here if you look at the figure, this is the 90 degree. Therefore, sine 90 equal to 1. So we get expression mu naught IDL upon 4 pi. Okay. So that has already been described. The semi-vertical angle made by, hello.